Shall we start?
Now to check the route, please. So whatever, but now you are in charge of the.
Can we start, please?
Welcome, Asif sir.
Hi, sir. Good evening.
Welcome. Dr. Roman, we can start now.
Yeah, I'm ready. Just let me know.
Yes, sir. We can.
Yeah, okay. Thank you so much, all of you, for joining this evening for our second day of training. I extend my heartfelt welcome and to Dr. Ashish Srivastav sir, who has been, pioneer in the research, especially for maize crop improvement, and he has a wide experience, especially for working in the international organization as well as working with the multinational companies. And now he is leading the corn research program of the Corteva, and probably not for all segment, but he is one of the pioneer maize breeder working in our country. I request, sir, please share your experiences on the maize breeding, especially how we can have the AI into the integration in the plant breeding so that we can improve our efficiency. I request all of you, please listen him patiently and keep your 2 or 3 quick questions ready so that you can get benefited. So, sir, floor is now yours. I request you to kindly deliver your talk.
Thank you, Dr. Sel. I think first of all, thanks to the organizer, USL, and then IMR for providing this opportunity. So, and this is, I am really delighted to present here whatever little knowledge I have it. So, with this, I think just my, if you look at that thing is, my name is Ashish Srivastav, and then I'm basically a corn breeder. And I started my career with CIMIT for almost 5 years. I worked for the CIMIT based in India, and then work for Monsanto, which is currently a buyer, and then moved to the Corteva, which is a legacy of a pioneer. So we have a throughout experience of corn. So and currently I am just India level. We are taking care of post-rainy corn. This is my brief introduction. So I have almost 25 years of experience on corn. So today the topic was allotted to me is the AI assisted breeding. So I will try to do the justice with that, whatever we know, and we work closely on that. And with that knowledge, I don't know what kind of audience is there, but I assume is the breeding community and corn community. So I will keep my presentation towards moving on breeding side and how we can exploit the AI in that front. And then the AI is really a vast topic, but we'll try to cover it within a limited time, whatever best possible is there. So I think I have a time till 5:45, so I will try to complete within that. So I hope my slide and everything is visible to everyone, and then my audio goes very well on. Okay. So coming to the flow of presentation, if I talk about that, we'll talk about the AI, what is actually it means, and then how it is relevant to the corn breeding, and then what are the different domains, dimension of AI, and then how we can use it in our breeding. Especially I have taken one case or one example of the complex trait, especially drought, which is nowadays is very relevant in the corn breeding. And then what is the going impact in future? Is there any change in corn breeding or any modification or any addition is there? So you will see in the subsequent slide. So coming to that, my first thing is what is the definition of AI? So I think most of the people are knowing this. There's nothing new. So it's simply ability of machine to simulate human intelligence, such as learning, reasoning, problem solving, and decision making. What it uses a lot of data and algorithm. So how it works here? So suppose for any human being, if you identify the particular human being, it has to be different traits. When you combine that trait and put it under one umbrella, then it's make that person's personality. The same way here also what we are doing it, we are giving a different ingredient, different inputs or data to the system, and that get analyzed and come to the conclusion of whatever the good or bad or average, it will come up in that way. So whatever it try to use that as a human intelligence, and then we use computer and robot which gets the data, take the data, analyze that. There's a lot of steps involved, a lot of modeling involves, a lot of algorithm is made it here. And finally, we'll get at a smart decision or action, what we need actually. So is that is depend on how we do each step very nicely. We are classifying the things clearly. We are giving the right kind of input, right kind of data. There will be a lot of cleaning is required. When we do a lot of cleaning, then we'll be removing the noise. Where when we have a minimum noise, then we are going to get a better decision. So if we come into the plant breeding, using data and algorithm, we select the best genotype and in faster, efficient, and then more accurate way. That was our objective. We do the good thing in a better way, efficient way, so that our final outcome or return on investment should be well justified. When AI learns from the data, what data? It is whatever existing data is there or we have generated so far, and it uses that learning to make the better decision. If you come to the final is a one-liner statement, AI is a machine that can think, learn, and make decisions like human being. Now I'm being more specific to the corn breeding, which area it can help. So AI can support a lot of things on the data handling, how AI process large agricultural data set, which generally we only depend on the genotype and sometimes we'll go with the phenotype data. But there's a lot of other thing is weather data, soil data that can also be captured and used in decision. So actually the objective is we are not missing anything. Whatever the influenced factors are there, we try to put together in a one umbrella in under one machine and then give that information based on the existing data, how it then the machine will analyze how the things will be going to be and which one is good, and that even system will make a decision good or bad. And then corn breeding complexity. So we are most of the breeder or most of the trade which is simple trade, people are doing very good wonders on that trade. But when it comes to the complex trade, our speed or our accuracy becomes slow. So here it can do the better job also, even if things get more complicated, because the complex trade is always influenced by environmental, and then one of the biggest influencer is a year. Something may do good in 1 year but may not do good another year. So that kind of complexity make our life little challenging, or somewhere we are very excited this hybrid is good on this particular year, second year, or when we go or little change in environment, it gives surprises or challenges. So and then AI is also enhances the breeder expertise. AI accelerate data analysis and prediction, but the breeder has overall control. So it is not, it's giving you the option. Now you have to select which one way you want to move forward. And then for sustainable future, it is going to be one of the good offer or opening where we can use and deploy and get the better result. So I will touch some of the applications. So what are the areas are there where AI can help, and then in a tremendous way, which you will see. So by transforming plant breeding, it is doing that, making it faster, accurate, and data driven. So if I go at that application, it helps in the genomic selection and trait prediction. This is the one of the key area I have taken. Most of the people are working on genomics area, and selection is there, and especially the trait prediction. So we have, if you look at still the molecular breeding or conventional breeding, a lot of knowledge is available with us, and we are partly or deploying in that. So some cases, what it does is additional feature comes here is that when we have so much of information, can we use for future prediction? Why we need future predictions? There are predictions is required because when we can predict, then it has a lot of implications. Then we can reduce our other thing which we are not going to do that, like our testing. We need not to test all the hybrid. Second thing is, if we do early predictions, there is no need to go for even going for the final stage of the parent and then select it. So this is a lot of advantage. That's why trait prediction is required. But trait prediction is also, everything comes with the accuracy, what kind of accuracy you have it, your prediction accuracy. So in genomic selection, it's help AI help in a bigger way. We predict breeding things and line performance, enhancing the selection accuracy of corn breeding. Complex trait, there are the different models. When we build up a model, we'll see the model like different models. We compare the model, what are its accuracy, how we can, which model is best suited for our set of conditions, our set of data. Then we use that like yield, flowering time, stress is all complex trait, especially the stress tolerance and yield, which is more complex trait. And then without field evaluation, we can do that one. Accelerating breeding cycle, as I said it, we are with this AI things, it enables us to do the selection on the early stage, or you can say the segregating stage. Then we can do the selection. So which one will be we can using? And nowadays everybody is using DH. When the DH people are using, then with DH there is the number of families or number of progenies are more. The moment if we can select it at early generation level or early stage, then need not to be go with all lines planted and selecting that. Capturing the genetic interaction, it is because once you are talking about multiple trait, it has a interaction among each other. So we can predict with that, identify that thing. So selecting promising line earlier, it's really will save that time and cost. So that's one area of the AI in genomics. And second thing is where nowadays we are talking about a lot of data. And then in the beginning, I mentioned the data, whether we are not talking about the weather data, soil data, nowadays it is available. Either we generate it or we outsource from somebody. When we say that our generation, we can generate through our satellite imagery is there, or any site where they are providing the data, we can outsource. But that data will be used for our prediction or model building, we can say. So AI automated trait measurement, and that's how throughput imaging in some of the cases where we go for manual capturing of data, which is cumbersome, time consuming. But with this, like I'm given a picture of drone. So you have acres of land, but within a 2-3 flight, when you take with this drone, all data will be captured. And it's a matter of hardly a 1 hour. And then this overflying it on the above of the field. So like I can give the example of plant height, or sometimes people are taking the color of the things. As you train your model, you can fly for that trait. So, but initially you have to train your model or machine what kind of trait you have to give some input trait, then build up a model, that model will generate, and then you can do that. So nowadays, some of the traits are very well available in the public domain. You can go and use it. When the plant height, leaf area, all these traits are very much common here. And then early stress detection also, with the use of AI, you can detect when based on some symptoms, what are the symptoms are there, that symptoms is captured. So you know this is going to be a situation of drought or nutrient deficiency, or any disease spread is going to be there. Then you can take according some mitigation measures, or so that to avoid your damage of your crop. Consistent large scale data. So as I mentioned, with this, our manually, if you want to do it such a big area in shorter period of time, it is close to impossible. But with drone and other thing it's very easy thing. And though initially it is a cost, but later when you're running cost, if you look at that, it is very cheaper. So it is faster scale. You can't imagine with this drone data. So you can collect the drone. And then the most complex trait, when I talk about the interaction, G by E interaction, we are saying it, then it is tough. And then now when we talk about G by E interaction, it's, you know, that this is one of the toughest thing for any breeder to predict how my hybrid will perform next year. We are not sure until we see that thing on the ground. But with this help of AI, we can predict it, or we can simulate that condition, which we'll be seeing in future. AI in complex modeling, AI integrate diverse data and learn non-linear relationship to accuracy of more G by E interaction affecting corn hybrid. See, stress tolerance prediction, I also mentioned, like drought, you can also predict with the model. You train your model. This is my best hybrid. This is the worst situation, how it performs in that environment. That way it build up a model. So you build up 1, 2, 3 kind of model, and my model has all kind of things: worst case scenario, average scenario, medium scenario, better scenario, all scenario. And then you'll see the performance of your hybrid, how your hybrid is performing. If your hybrid is performing across the scenario, that's what you're looking for. So then that will be your ideal situation. And then you can go for it and then test only that. Something is showing in the beginning itself is like not moving forward, or it's not giving the good result. Why to go and field and test and put your energy behind it? So, and then climate resilient breeding. So this is also comes under the complex trait category. Selecting that hybrid based on the complex trait or stress trait, you can give your ranking of your hybrid parent and select that hybrid in different things. So with this, it will give you either sometime we go for different zones, because we don't want to be like a localized thing as an organization. Even for the multinational organization, we look for the hybrid which performs in a bigger geography. And sometimes we also go for, we call it as something if you want our hybrid working outside your country. how it is possible, because your country has some specific requirements, some specific kind of soil, a specific kind of management. The moment you go to the different unknown geography, you are prone to get all kind of surprises. So when this interaction or model building happen, you can at least some extent you will be sure that these are the suppose you have a set of 100 hybrid, or you want to be said, okay, no, just out of this prediction, I have selected only 20. So 20, I will go and put in a test there to get the further confirmation. But initial cut, I have already made. I have removed the junk. I have removed the noise based on my models, based on my data, based on my overall past experience. We removed everything, and then finally going with a limited thing. Let me go with so just coming to the what other things is there with AI, it can help in your supporting the decision. What decision? Suppose you have selected 20 hybrid, which hybrid rank first in terms of different stress environment? What are the top lines? What are the how we are going to optimize the trial? And reducing breeder workload. So this way, this helps. And then breeding for AI in breeding, AI accelerated breeding cycle. I think that's we already mentioned that it is faster, cut field trial cost, and improve accuracy in the complex trait selection. So whatever the limitation as a person or as a because of existing knowledge, whatever is there, it's try to overcome that up to some extent. We are not saying it's going to be 100%, because everything there is a lot of input required. As you move faster, better quality of input, then your output is certainly to be more of controlled. That is going to help. And challenge for the future outlook, challenge include data quality and technical need, future hold digital twins. So digital twins is basically when we talk about without testing or something, you are just creating an environment and testing that material there and finding out, oh, yes, I'm mimicking my situation, and that mimicking situation, my this certain hybrids are doing good. So then we'll go for that limited hybrid and test in that environment, and to get the final closing of that thing. Okay, yes, whatever my observation output was there from the AI model running, it is now working. And then within limited of hybrid, you can do better selection. You can be focused more. If you have to evaluate 100 hybrid versus 20 hybrid, certainly you will be do better job when we have to select the 20 hybrid or evaluate the 20 hybrid. Human AI collaboration, combining human expertise with AI driver, create data-driven decision for resilient corn hybrid. Just I have taken an example, as I mentioned, I have taken a case study for the complex trait drought. What steps are involved? I have mentioned a lot of algorithm is there. So how it works. So earlier if you look at that data collection, I think everybody as a breeder or a scientist, we do a lot of data collection. So far we were doing the phenotypic, then we entered in the area of genotypic data. Now the third domain has come up also. We have to generate the data for environmental data also. Then earlier we were looking for G by E. Now we are looking for G by E and management or environment, all things we are just including it. So we are not leaving that error, we are trying to reduce. Unknown factor we are going to reduce, so that our chance of success or prediction accuracy should be better. And then with this set of data, we'll enter in the model. So what model learns? Based on this data, model learning is happening. So which genes are giving better yield, or which QTLs are giving the better yield under stress or any kind of new environment, which hybrid perform maintain better or giving the less reduction in the stress, and how environment to modify the performance. So is adversely or supporting or any challenges, what we miss it. It's like a cyclic process. We input the data, then we run the model, and then we see the output. Then again, if something is missing, we can go back and correct it and again come back. So coming to the machine model or machine learning, I think most of the people are now using the machine learning model. So with machine learning, we use random forest, XGBoost, deep learning model, neural network has been deployed in many other cases. It depends on the case by cases, and genomic production model, it has been used also. So now the third step is what is a prediction phase. We have all the, so as like a human, I can compare as I make a analogy. If I'm a breeder, I have all the information. Okay, I have certain lines are doing good for certain traits. This is input, it comes to my mind, but my mind has a some limitation. I can't capture thousands of line in my mind and get it ready as when it is required. Otherwise, I have to go my notes and other thing. But with this, we keep feeding on that. Okay, this is the things, or any good line you have to select. These are the certain criteria. And that criteria, based on past, we have already given to input to the system, and system has already recorded and make a clear-cut decision. Okay, if I am getting XYZ things, then this is considered to be good. If something is missing or rating is not good, then I will not rate that as a good habit. So based on that information, that it will decide the ranking under the drought cases, what is the ranking of that hybrid, and from the tolerant to susceptible. Actually, our target is to get the tolerant or less reduction in the field as compared to the normal scenario. And then yield under stress predict performance in low rainfall area environment. So that also can predict it because we can simulate. Stability, that's one of the important area when we talk about the stress environment. It is one of the biggest concern because sometimes we get peaks, some can get a downside and upside, but it's not stable. So stability is one of the important trait we will be prediction is there. So this is the main area of AI when we are giving a lot of data, and then with the machine, it has a lot of opportunity to digest so much of data and analyze it, which as a human or as a single person is very difficult to do that, and kind of accuracy is there. So I will share some of the slide where you see where the difference coming from. What are the area it is a difference. So again, one more new dimension has come up where we are talking about, so for whatever first two steps I told, it is already happening. It is smaller scale, bigger scale, depend on the organization, depend on the person, it is happening some way. But the prediction phase is one of the things new, which is AI related things. And it is going to be help a lot because in some of the organization we are already using, or we are decided to move in that direction, and so that it will help. And when we do the prediction, then only we make that crosses, something is good or not. If we say this, my X by Y combination is not good, why I will go and make that process? But I'm sure that X, Y, and Y is going to give me a good hybrid, then only I will make that process. So it will save a lot of resources, energy, and then whatever the energy time is there, I can use for the better thing or some other input things. So coming to the last is a fourth is a simulation. So which is basically, I already mentioned the G by E interaction. So once you have that information, because you have captured your genotype, you have captured your phenotype, you have captured your surrounding, which is basically your weather data, your soil data, everything you have captured. So chances are that you can play with these information. So you can say you have your rainfall information, you have your temperature information, you can play around. If tomorrow, like if I take this example of this year we are going to expect the El Nino. Basically, we are expecting 90-95% rain in some area and erratic rainfall. So with that, which of my hybrid may be doing better? I can simulate that kind of situation and give the system that information. Okay, in this given situation, this year rainfall is going to be limited. What other hybrid can perform? So that kind of work can be done. Or tomorrow, all of a sudden, I can say I've decided maybe this rainfall is going to be 20% less. Now we are talking about only 5-10% less. We need furthermore, water is going to be a limiting factor. If your root zone is not having the water, then what could be the scenario? Which hybrid can work there? So this simulation can work on this direction. This help in pre-field decision making. So once we decide that, okay, this situation, because this now prediction of weather is also very common, we come to know very well in advance. Using that information, we can play around. And now this, and also if we want to predict my hybrid is working in A zone, will it work in B zone also? Or A territory it is working, when it will work in B territory also, that also we can predict it. So that's a good example. So now I will be moving the practical approach, how it is different from what we are doing it. So we are quite successful doing where we are doing it, but what area it get changed. So these are the aspects if you look at these are the major area, it is getting it changed. So decision bias. So whenever your human things are involved, always the biasness comes. It is, we are all human beings. We are prone to make a mistake. So nothing surprise to us. But when we go with the system, with the data-driven system, the chance of biasness is much, much lesser. Speed, of course, we mentioned that. Selection method, here we are talking about the phenotype based or visible trait, whatever is there. But here we are talking about the combined effect on the particular hybrid or genotype. Trait load, we can select the large number of hybrid tested there. AI reduced trait pre-filtering using AI. So here also we can reduce trial. So basically we can reduce the number of trial here unless you don't know what is going to be. But here we can plan it and reduce our load. Accuracy is certainly better with AI. Handling G by E as a complex trait, this is better. Trait prediction is better for before testing. That's what I said. It predictive is a new area which has come up there. So that here prediction is impacting your testing, your decision, your implementation, everything it is going to impact. And then labor requirement is certainly less. The last point, when you talk about the cost, yes, the high, if you look at our conventional way, there's a lot of cost involved because you go plant, capture all the data, manpower involved. But here, initial cost of your capital is high. But when we look at the long-term running cost is pretty normal, so not much. Then this is, we said that conventional breeding is pretty old, but now we say that everybody has moved towards the molecular breeding. So does any change in molecular breeding versus AI, or still both are same, or what are the differences? Yes, there is some differences are also there. So which you can also, I have mentioned the more of the trait, but you can say some of the focus area is only for specific genes and marker. It is targeting, identifying, and selecting. But here it is predicting overall performance and then trait as well. So data use, so it's only genomic data, but it's all is a mix of all traits it is using. And decision, it is on the gene or marker level or QTL level, but it is whole plant basis. So likewise, other traits are there. You can look at the traits and you'll see some of the difference. And here it is, data is very important in case of AI. And when I talk about the data, it is also shows is the quality of the data. We often hear that garbage in, garbage out. So if you want to really do a nice job on your prediction on that, because a lot of investment, lot of energy will go on this side, unless you have a better input or cleaning of your data is not robust, then don't expect that things is going to be better for you. So let's use that first-hand information or data, understand data, what is going to be there, and data should have a minimal noise so that you can go and say that, yes, whatever data I have entered in the system, then because system will simply do the process. It doesn't have its own mind. It is based on your input. It is creating some kind of conclusion. If your input is not correct, then it is not going to make a good conclusion. And that conclusion is the basic of your prediction. If I'm saying good line, actually good line is saying as it is really a good line, then the system will understand it is a good line or good hybrid. Then based on that, it derives certain information. Okay, something coming to similar or something coming to the better than this, you will rate better than that. Otherwise, what will happen if he himself is his system is confused because of sometime I'll say this is also good, this is also good, then system will kind of confuse and then your accuracy, it will not be there. So coming to that, when a new thing comes up, I think a lot of advantage, but same time, I just put it, what are the AI advantages there and then human advantage versus some of the disadvantage I have listed. So these things are already throughout my presentation. I'm talking about data, handle massive data it can handle. Speed, fatigue is not at all attached with the system. Accuracy, biasness is nowhere there. Automation, you can give one task 100 times, it will run. But as a human, if you have to do the repetitive task, you feel fatigue or bored or something else, other thing will. But when you come to the human side, what is missing here? Advantage there is a field knowledge, past experience, but sometimes it can judge beyond the data also. So this is one of the advantage, but we have to somewhere trade off. Sometimes what we are going to get and what we are compromising, it always a trade off what we have to select. And then creativity and innovation piece is missing, because whatever we give to the system will analyze and work on that. And then context understanding, as a human being, we understand better of concept, what is the farmer need, what is market demand, what is the local condition, we understand better other than the machine. Flexible decision making, so we can adapt quickly when the condition changes. Any sudden changes, I can give the example of FA. Maybe a few years back, we were not aware of what is FA, how much damage it can cause to our system or crop. But within a short period of time, everybody worked together, they generated the information and then work accordingly, how to manage the risk of FA. But system will wait for the data to come in the system. Okay, yeah, this is FA. Oh, this much damage it can cause. Then it can help in prediction. Otherwise, it will take its own time. And problem solving, when you have a less quantum of data, probably sometimes it says insufficient data or less data also will not give. Likewise, we do more replication, it gives better result. So if your data is not enough, it can't do the right prediction. Some disadvantages also there for the AI. So it's like data dependent. I mentioned already, limited creativity, setup cost is high, and complexity. And then human, that, so there's not more that. So just one, if I have to summarize on that, the practical aspect of AI. So traditionally or conventionally, or you can say right now what we are doing so far, we test 100 hybrid in the different environment. I'm not talking drought. You can take it any field screening also, or yield trial. It takes 2-3 seasons, and then you select some of the best hybrid, which we do, and then it has goal in a coordinated trial also. You can say the same way it happens also. You have to test 3 years, and then year after year do the advancement and selecting finally the top hybrid which is performing better than check. But when we get the support from AI, so what train AI will based on our data, whatever the past year data. I think in some of the cases, people are the organization is having the 100 year of data also. So with that data, we trained that our system or model built on the data, and then we predict only this. We are going to make these 20 crosses only, and these 20 crosses will be tested in field and getting selected these top 5. So output, if you look at that, the both way is the same. I'm finally reaching to the 5 hybrid, but the effort we put it in the 2 ways is much less in case of AI supported breeding. But a lot of background work also goes in that. You have to always keep in that mind. And then what it comes out of that, it is a faster selection, lower trial cost, better accuracy, same result, faster and cheaper. So this is just an example I put it there, how AI is going to change the things or benefit the things. So when we talk about this optimization and synergy, how we are we looking at one thing is going to change everything, or other thing is become irrelevant? No, this is not going to be scenario. They are not competing approach, they are complementary. So you have to build that nothing, whatever, because we have to generate the data, and data has to come whatever way we are generating. Like whatever, be it molecular data, be it phenotypic data or genotypic data, what data is there? So far, we have to generate and put in the system. And the best modern breeding pipeline will be molecular breeding, will identify useful gene and marker. AI model, the predict best combination and performance. So this is everything is going together, and field trial that's our normal way we do the field trial and validate that result. But here the effort is getting the shorter and shorter, lesser, and then what combines, when you combine both of the things are there, you get faster and more accurate breeding research. So this is my last slide. So if you look at the summary and way forward, so I think is going to be breeder plus AI working together. So this is the way it is going to be, how it is there. Conventional breeding reliable but slow on resources and resource intensive. AI-based breeding is faster, smarter, and data-driven. future trend is hybrid approach. So as if you can take the example when conventional breeding was there, then molecular breeding came in, then we decided to go together. And then we got benefit of, now this is a new area has come up. If we combine that, we can do lot of predictions, lot of simulation we can do, and which helps in reducing our cost, working on the ground, getting massive data collections. And then, so if you look at some simple analogy, an experienced breeder who has analyzed millions of trials result and can instantly predict which hybrid will perform best, survive better in stress. This was the outcome of my slide. So I think with this, I'm towards the end of my slide. And thank you, everyone. And then I think I try to cover the basic and practical approach as a breeder, because I also consider things are new, but if we understand the logic, then we can go back in each area. If I'm looking interested in model building or certain things, if somebody, what model works, how this model need to be prepared, then we can go deeper on that diet. And somebody is looking on like phenotyping or through high throughput things, then we will go in the direction of the capturing the images, and thousands of images we can capture and build up a model. That model will help to generate whatever the trait we are looking for. At least if I am looking like a human, somebody, I have to tell the system that a human looks like this. Then system will understand, okay, this is, if something picture comes to look like this way, it is like a human, or maybe a square or a circle, whatever you want to do. So this is a simple example I'm putting it. So that's all, Dr. SL, from my side. If anybody has a question, I can answer based on my limited knowledge.
Yeah, thank you so much, sir. Yeah, it was wonderful lecture. We all agree. We can have a virtual thumbs up and all other emojis. You can play it so that everybody will be get excited to have our better things. Thank you so much. We are getting different kind of emojis. Thank you. After this nice lecture, I think many of you might having questions. We can have 2, 3, 4 questions. You can raise your hand, or you can put your things in the chat box. We will be able to answer. Please raise your hand one by one. We can call. So in chat box, could you please share any practical application example which you have personally used in your breeding program? For example, trait prediction or genetic gain prediction using AI. So this is one question from Aditya Pratap Singh, sir.
Yeah.
Yeah. Yeah. Okay. This is one.
So I think there's a couple of examples there. I think I mentioned one of the trait plant height. So which is nowadays is very much possible, and practically people are doing it also through using the drone. And then because then you have to be trained your model. We have already trained our model, and it is already happening. So this is on practical side I'm talking about. And then other thing is also we have seen that identifying the crop acreage, if you want to do that, how much crop by variety, which variety is covering how much area. So if you have to build up your model, you can identify the corn is planted so many acres and like that. Another crop is also possible. So I think we have already, in practical way, we have added many traits in the system which we are deploying as a organization. Yeah, I think it's a multi-year data is always good. It is from Aswin. So of course, as a breeder, we also, Doctor, you are on mute, or I don't hear you.
Okay. Yeah, no issue. Please
So,
go ahead.
I'm listening,
talking,
Doctor.
yeah. So no, I'm saying it. Dr. SL was on mute. He was talking. So I think is multi-year data for Dr. Aswin. It is multi-year data is always better, because then you captured well of your environmental information. Otherwise, 1 year environmental information will not same than another. Yeah, I don't see any question. If I miss anything,
There
I
is
think
few questions in the chat box. Probably your lecture is so exciting, and people can hear this lecture again on our YouTube channel. Thank you so much, sir, for accepting our request despite your great busy schedule. So if we are able to catch you out of that, thank you so much, and wish you very best from our IMR side, IMR family, and we will be love to hear you again at the upcoming international match conference. Thank you all. Now, thank you, sir. You may leave now this platform, or you be there. We'll be having our next lecture again on this similar kind of the topic that will be delivered by Dr. Mukesh Chaudhary. I think Mukesh have joined. Dr. Mukesh, you can switch on your video so that yeah, we can follow you very nicely. So Dr. Mukesh is a senior scientist plant breeding at Indian Institute of Maize Research, and he has recently done his PhD from Australia, and he's one of the leading pioneering scientists who've been assigned the duty of the genomic selections and other things at IMR, and doing a quite innovative work. So we look forward for the exciting talk from the Dr. Mukesh. Dr. Mukesh, now floor is yours, and you may share your talk. Thank you so much. All.
Yes, sir. Yes, sir.
Yes, thank you, Washington, for introducing me. I'm just rejoining again. There is some problem with my screen.
That woman, we have still 117 participants, which we need to look into, and whosoever are unable to attend it, please share a mail today what we discussed during our planning.
Sir, we have increased the capacity, sir, up to 500, sir. So anyone can join in this one. We have 500 capacity, sir.
So they can invite their friends also.
Yes, sir.
Okay.
Sure, sure.
मुकेश सर तो मेरे रूम
ये भी है दिख रहा
yeah, it's visible. Yeah.
So, good evening, everyone, and thank you, Dr. SL sir and Dr. Raman sir, for providing me this opportunity. Actually, I haven't been like a kind of extensive expertise on this topic, but like I have just initiated a program of genomic selection, like around 2 years back after completing that and joining this institute like after my PhD. And there I did some work related to some genomic selection. It was not core genomic selection. I think someone is writing in the screen. Roman sir? Hello. Am I audible?
Yeah,
Yes,
you're
yes,
audible.
yes.
Should I continue now? I think some sketches are coming on the screen.
Now continue, please.
Okay.
You can make slide share mode. I think in your PC it's coming 12 slides. What could be the next slide is also coming over here.
Okay. It's in slide show only. Let me go. is it visible now? The entire slide?
No, not
सब
visible.
जगह बच के आए
Sure, Dr. Saab,
इसके
you
मैट
can
में
go
पानी
to,
है
you can go to top display setting is there. You click on that.
तो जूता भी खराब होगा
Just a second.
Yeah, just click on that and go to second one. Select the second one.
So now it's fine with everyone.
No.
Is now the
Yeah, yes, it's okay. Yes, okay, good.
Okay now.
Good.
okay. So
Okay, sir.
again, I welcome you all. So the thing is like the topic that I have been given is why we need this genomics-assisted strategy for enhanced breeding efficiency in maize. So as we all know that although with the conventional breeding, a lot of progress has been made, but the thing is that that progress has been just like, okay, we can compare it with the kind of transportation. Like transportation started with first as a walk, and then it started with the cycling, then it went to the cars, and then now we can see that there are bullet trains as well. The same is the case with the breeding as well. So the conventional breeding has given us a lot of products, but the thing is that the progress has been quite slow. So that's why the topic that I'm going to cover is like how we can make that progress faster with the help of the tools that are available in the era of genomics. So if we see at the evolution of the breeding, how the breeding has evolved, so we all know that the breeding started with the experience of like farmers started it, and they used to select on the basis of experience. So that's why we call it as like breeding is not only a science, it is also an art. So it started with the selection on the basis of experience. Then the experimental things came up. That was the second phase of breeding, in which we can see that there was Mendelian genetics involved, and then there were some like crossings and selections. All those things started, but over the time, the third phase of breeding started with the advent of like how the new technologies like the genomics, the sequencing things came up. And as soon as we got the molecular markers, the third phase of breeding started. So we can see that the events at the bottom of this slide, you can see these are the most significant events that happened, and that led to the evolution of the breeding phase 3 over the time. And we can see that in 1992, RFID markers were used to the marker assisted selection in May. And then there was also like the talents in maize when haploid induction genes were also launched. Over the time, the molecular biology has also evolved. So it has given us many options that can be used to accelerate the genomic breeding. Or we can say accelerate the maize improvement for the different fields. And as Dr. Srivastav has very well explained in his presentation, so the next phase that has already initiated, which is at infant stage, is the breeding phase 4. This will be based on AI, artificial intelligence. So coming like what are the limitations of plant breeding and why we need these genomic tools? The thing is that if we see at the growth rate of the population, we need to feed around 10 billion people in 2050. And with the pace of the conventional plant breeding, it is not possible to meet these targets. So with the conventional breeding, we already know that this is just a B, that we have to test exemplars in our target population environment, and it goes through the multi-environment trial testing. And based on that phenotypic performance prediction, we go for the selection. And it takes a lot of time. It is affected by weather. It is affected by environment and other factors. So the progress that we expect, it is quite slow. So it is just like we have started just like the cycling phase of transportation, as what we can say, we are just moving on to the car side. But now with the genomic tools, we need to aim for the speed of like bullet train. So the other limitations is like when in the conventional breeding, as Dr. Srivastava also said, that we have to evaluate a large number of lines. What our process will make, we have to evaluate a large number. And to evaluate that, our cost of phenotyping is too much. And this cost of phenotyping, if we see in the current scenario with the genotypic options that are available, it is expensive than the genotyping. That means like with the less than around 10,000 rupees, we can go for genotyping of a single line. So we can go for selection of that line, and if we go for multi-location trials, and if we go for phenotyping, then the cost will be way higher than our genotyping. So that is also one of the limitations. And the last is we can't make it as a limited throughput, like because we have to evaluate a large number of lines, we have limitations of the land, the time, and the human resources. So first I'll just give a brief overview. So I don't know like how many participants are from the breeding background, but I'll try to explain in a layman language. So this is like breeder's equation. If you see, we can correlate with any breeding program, whether it is animal breeding program, whether it is like in plant breeding programs, or we can go for forestries, to anywhere. So the main thing is that like if you have to see at the how the genetic gain is achieved over the time in the breeding program. So it depends on 3 numerators and 1 denominator. So 3 numerators, 1 is the selection intensity. That is like how much of the total population that we have started, what proportion will be selecting to make cross or to advance to the next generation. So the second is selection accuracy, like how well, how without error, or how precisely you can select those individuals, and those selected individuals, how they will be passing on the additive genetic variants. That is the possible or heritable genetic variants. And the last and the denominator is the years per cycle. So basically, years per cycle, it is our generation interval. So the main objective of any breeder is to increase the selection intensity, to achieve higher genetic gain, and to increase the selection intensity, we can go for like, let's say like out of 1,000, we have to select only 10 or 100. So we have option. But if you go for only 10, then there will be too much stringency, and there will be chance of reducing the genetic diversity over the time. So we need to make a balance. So maybe we can go for 50. It depends on what resources we have available. And again, to increase selection intensity, we can go for a bigger population. The founder population that we are starting with should have a larger population size. So it helps in increasing selection intensity. Selection accuracy can be increased by using more number of replications, and it helps in reducing the environmental variation errors. So we can correct for environment. So that is basically the selection accuracy. And then genetic variance is like we should start with. For the genetic variants, like we should start with a diverse population that we are starting. But in diverse population, we should always focus on what is our target trait. That is what is our objective to improve. Let's say like, because sometimes if we want to improve one trait, there can be a problem of linkage break, or there can be an unwanted trait in that population. So that's why it is mentioned like genetic variants, we have to be slightly careful. What is the genetic variance for our target rate in our founder population? But it must to increase selection accuracy. And the last one, which is the most important, because these 3 are very difficult to control, but the last one is like we can achieve faster genetic intervals with the help of the tools that we have available in the current context. So I'll be talking about those as well. So that is like how many years per cycle of selection it takes. So in conventionally, like it used to take 3 to 4 years to complete one selection cycle, because we'll start with making process, then we will evaluate, we will do some test process, we will evaluate them, and then we'll go back and start again, like what are the parents that were the best based on test cross performance, and accordingly we'll make a cross and start again. So it took a lot of time, but it can be decreased with the use of other approaches that we have, like seed breeding, then we have DS technology. So these are the tools that can be used, and it has helped immensely to reduce our generation interval. So the denominator is the key part that the breeding companies and the breeding programs take care of. So just the like genomics, we are talking about genomics-assisted strategy. The basic strategy that started was like PTL mapping. So PTL mapping is basically, it starts with the selection of 2 diverse parents that will be crossing, and then selfing to generate maybe the different types of mapping populations, F2, reals, or maybe BL. then we genotype those populations and we phenotype those populations. And by just doing some statistical analysis by correlating our phenotypic and the genotypic information, we identify some genomic regions. Those we call as like QTL. And those important QTL are validated, and then we target for the integration. So validation is must, but like the limitation of this approach is that it is based on only on 2 parents, so there is limited resolution. And the main approach is like it is mainly used for like coarse mapping and then followed by fine mapping. But the other approach, like the GWAS, it has given an advantage that in that case we have only 2 parents, so we have limited diversity. But GWAS is based on a diverse panel. That means like we have nearly like 300, 400 diverse inbred lines. We can go for genotyping of those, phenotyping, and then we can do a statistical analysis, and we can identify which are the most important markers that are linked with our target trait. And once we identify them, then we can go in depth for identification of what are the candidate genes that govern function. Let's say I talk about drought tolerance. So if there is any gene that has been identified to be linked with our target trait, that means we can use that, we can target that candidate gene for use in our breeding program. So that is the like overall the comparison of both approaches, but there are some limitations. So that's why we'll be moving on to the next. How like there are some successful examples of these both approaches. On the left side, we can see that these are some of the major QTLs or genes for the different traits, like quality traits, flowering time, abiotic stresses, or quality like opaque food. So these have been identified through the QTL mapping approach. And the right side one shows the successful examples of the genes which have been identified through the GWAS approach in maize. So coming to the main expertise of mine is genomic selection. So why genomic selection? The thing is that the limitations of QTL mapping and GWAS is that we cannot use all the markers. We can use mainly the significantly linked or significantly associated markers to the target traits. But with the availability of cheaper sequencing platform, we can generate a large number of market data, and that large number of market data, let's say like we have 2,000 markers, so we can use those all 2,000 markers without need of having them significantly associated to the trait to estimate the breeding value of the individuals. So basically, if you look at the definition, so we use genome-wide market data, and what we estimate is the genomic estimated breeding value. We call GEBVs for the individuals in our breeding population. So for that, we will use a model, and that model will be based on a training population. And that training population will have both genotypic and phenotypic data. And those genotypic and phenotypic data is used to make a model. And that model, once it is trained and once we use it, refine it, then finally we test it on our breeding population to estimate. So in breeding population, the main thing is that in breeding population, we don't need to go for phenotyping of all the breeding population. Maybe we can go for 10% of the entire breeding population, and then we can validate it with our training model, and then we can refine that model as well. So this is how the genomic selection works. And in the next slide, I'll be explaining it in detail. So then what we do with these GEBVs, once we have these genome estimated breeding values, then we use these GEBVs to select our best parents. So we will be deciding like, okay, we have our total like 200 lines. Out of 200 lines, I have selected top 30 lines with the highest GEBVs, and now I can use these lines for crossing program. So this is how like our genomic prediction model is made. Then we predict all marker effect of all the markers that we have. We don't go for like, okay, we should go only for the significant associated. And once we have all the effects of those markers, the summation of those gives us the genome estimated breeding value of individuals. So the basic is, we can see that we have a training population. In training population, we have both phenotypic as well as the genotypic data. And once we use that data to develop and train our model, so we have a prediction equation from that training population data. And then we use that prediction equation by using only the genotypic information from the testing population. So what we have saved here is we don't need to, let's say we have 1,000 breeding lines in our breeding population. So we don't need to phenotype all those 1,000 lines. Maybe we can phenotype a subset, or maybe without phenotyping, we can only genotype those, and based on what are the genes combinations in those lines, we can predict their phenotypic value. That means like we have taken yield data in our training population, but we haven't taken yield data in our testing population. But we can predict that yield. We can guess that yield with the use of the marker data available, which is common across both populations. So this is the overall scenario. And the main, we can see down is there, we will predict and select the best so that we will be shifting our genetic gain to the positive side. So if you see that the right side, this is also denote the same, that we have selection candidates, we have training population, and then we go for using some statistical models, and we select the individuals based on genotypes, not on phenotypes. That's why we call it as genomic selection. So what is the edge of this, and when to choose? Like we have three options. We have genomic selection, we have genome-wide selection, we have QTL mapping, we have marker-assisted recurrent selection, we have marker-assisted backcross breeding. So we have many options available, but the thing is that we need to decide, like conventional mass that we say marker-assisted selection. So genomic selection is advanced approach of the conventional mass. In conventional mass, we go for only limited QTLs, introgression of limited QTLs. That is like 1 or 2 major QTLs we will target, and we will go for introgression of those QTLs. But in genomic selection, we need to select as many as genes possible with our resources, and then we will use all those genes for the improvement of our population. So if you see in the left side, you can see the top part of this diagram shows that in phenotypic evolution, we go for crossing with test, then we evaluate test process, then we go for selection based on the phenotype. But if you see at the lower portion, that is genome-wide selection and mass. So in genome-wide selection and mass, we can select, if we have genotypic data, we can select even before flowering, and we can save time. So that is the main objective of saving time. That is like we don't need to wait for the harvest or produce of our test process and then go back and start again process. So here, if we have genomic information, we can start planning our process before even flowering, so we can save our time. That is like the idea behind reducing the generation interval. And then we have mass is not suitable for quantitative traits, and mostly our economically important traits like grain yield, or maybe we can go for grain yield under different abiotic stresses. So those are like complex traits. So those are not governed by a single gene. Those are governed by many genes with smaller traits. So that's why mass is more suitable there. So in that case, we have to go for genomic selection. That is the best approach. And why we should go for genomic selection is that, like if we go for conventional breeding, then in that case, we have this L that denotes like what should be our selection cycle time. So in that case, we have like 3 to 4 years, but here, like once you have closed your parents, and let's say you have made diary of 50 diverse parents, and then you have genotyped those F1s, the progeny, the hybrids that you have obtained. Then based on genotypic information or your genomic prediction model, you can go for the initiation of the next selection cycle here. So it saves your time. From 3 years, you can come to like 6 months to 1 year. So that is the advantage. So it helps in reducing the breeding cycle time. So that is the important point to be considered. And how we start? We start with, as we discussed, that we have to develop the training model. And based on that training model, then we go for prediction of the lines that are in your breeding population. So breeding population is your population which will only be genotyped. There will be no phenotyping, and it will be genotyped with the same marker data that you have used for the training cell. And it should be derived from the parental lines. So we say that, okay, when will be the prediction better? Prediction will be better when your breeding population is closely related to your training population. So that is the basic. So this is, we can say in a layman language, we can say that we can predict we can predict humans with humans, but we can say we can not predict humans with the data of plants, or we can say in any way, like we can predict apple with the apple germ plant. We cannot predict oranges with the apple germ plant. What makes a good training set? So first is the most important trait, as Dr. Ashish Srivastava also emphasized, that the main thing is that these things are just tools to assist our conventional phenotypic trials. So the foundation of any genomic selection program starts with the precise and robust phenotypic characterization in target population of environment. Let's say the target population environment is my drought. So if I want to go breed for the drought-prone ecologies, then that would be my target population environment. So I should have the data, phenotypic data on my training population in those environments. So that is the most important aspect. Then second, then you have to, the germ plots that you are using, I have already said that it should be related to your selection candidate. That means it should be related to your breeding population. So breeding population and training population should have closeness in terms of genomic information. Then size, so there should be optimum size of like over 300, and diverse germ plant, because if we start with a less diverse germ plant and if we go for prediction, then in few years we will be ending up with very less genetic diversity. Then increasing the model training set size. So sometimes if you increase model training set size, it helps in increasing the selection accuracy. And the most important is the genomic selection accuracy depends on your effective population size as well as the heritability of the trait. If the trait is highly heritable, you will have better chances of accuracy. And one more thing is that it's not like we have made a genomic selection model and it will work lifetime. Once you have made a genomic selection model, it will work for 3 to 4 years, depending on what reference population you have taken and how close the breeding process that you have, breeding decisions you have made for making process in breeding populations. After 3 to 4 years, the genetic relationship of those breeding populations will start deviating from your training population. So after 4 years, you have to bring that data back in your training population and you have to update that model and then start again. So that is the approach that is being followed. Then number of genome-wide markers. Sometimes we think that more the number of markers, it will be better, but it's not like that. The main important point is that there should be optimal set of markers, and it depends on some of the factors, like what is the rate of LD decay in the population, or in your crop, like let's say maize, your post-pollination crop, your LD decay is higher, and self-pollinated crop is lower. So in our case, made like being more marker, and there should be, like if you see any segregating segment of the genome, there should be at least like one marker. That is like ideal situation. And then it depends on your genome size. Like let's say genome size of maize, and if you compare with rice is very small genome size. So maize will being cropped with larger genome size will require more number of markers. And then low collinearity between markers. Let's say we have 5,000 markers, but 1,000 markers are quite closely related. So that means those will not add much value. So we should we should drop the markers which are having low collinearity. There should be low collinearity. There should not be high collinearity, which these markers with low collinearity. And we can see from one of the studies that if you see at 2,000 markers, after 2,000 markers, we don't see any increase in the selection accuracy. So it is just like it is getting stagnant. So that's the case in grain yield, and the same is the case like with around 2,000 to 3,000 markers. In protein content also, if we increase the markers up to 9,000, we are not seeing any increase in the selection accuracy. So what are the advantages? So advantages of genomic selection is like we have greater genetic gains per unit time than phenotypic selection, because we are reducing the generation interval. We are selecting before flowering, so we can attempt those process as well. We are saving the resources in terms of like phenotypic selection. So second is it increases the effectiveness of selection, particularly for low heritable traits. As I already mentioned, that high heritable traits can be easily selected with the phenotypic selection, but in case of complex states, we need to use the information from the genomic markers, because genomic markers, they are like environmentally neutral, but the complex states are environmentally affected. So if they are environmentally affected, there will be more chances of making wrong selections or low accuracy just by phenotypic selection. But with the help of genomic markers which are environmentally neutral, they help in increasing the selection effectiveness. And next is it helps in reducing the inbreeding depression and loss of genetic variability, because let's say we have 50 parental lines that we have decided, like, okay, with the highest genome estimated breeding value. So maybe out of those 50, number 1, number 2, number 3, the top 3 may be quite closely related, but they have highest DBV. So to avoid the loss of genetic variability, the breeders can go for choosing the cross of first with fourth, because maybe fourth is less genetically related to the first, second, and third. So the selection decision can be made to avoid the rate of inbreeding depression in our breeding program. And there is an approach like optimal contribution selection, which takes care of these things. Like once you have decided based on genome estimated breeding values, what are your predicted grain yields. So before going into the crossing program, we can put a filter on what are the genomic relations between those selection 50 selected lines, and then we can make the conscious or advertent process to avoid higher rate of inbreeding depression. Then we can shorten the length of breeding cycle, as already discussed, and it helps in selection of hybrids, because if you have inbred lines, we have data, we can predict the performance of the hybrid source as well, and accordingly we can reduce the number of processes. We can just narrow down, like, let's say I have to make 1,000 processes. Instead of that, if we have inbred lines, and I can predict, okay, these 100 processes will be my best ones, then I can go only for those 100 best processes. Then it allows GBV estimation even for traits for which they have never been tested. So the thing is that sometimes when you have tested and made your model on some traits, then you already know, like, what is the marker effect for those traits. So then you can use those marker effects for those for the prediction of those traits even without testing, like without phenotyping. And this is especially important for the traits which have like higher phenotyping approach. And some of the factors that affect that we should know is like what is the size and genetic diversity. It affects, we already have discussed. Heritability of the traits. So if you have complex traits with low heritability, so there will be chances of lower accuracy. Then marker should be in LD with the QTL. So that is one of the, if marker is in LD, it will be better. So there will be no recombination or less chances of recombination. Then which method of estimation of marker effects, which are, so there are different methods. Like some methods assume that all markers have equal and small effects, but some methods of estimation assume that some markers have lower effects, other markers have higher effects. So it depends like which method. So generally what they do is they test 3 to 4 different methods, and based on the selection accuracy, they propose the best ones, which one they are getting. Because it depends on what is your genetic constitution of your population. Then there is kinship problem as well sometimes in this. So these are some of the factors that we need to take care. So this is like one of the recent papers, and one of the recent approach that is being followed. Like it is not that too much old. And the thing is that how breeding companies are saving their resources and how they are evolving their strategies in breeding. So if we know that that maize hybrid breeding is a multi-stage selection process, and we generally go for haplotic pool. So we have like pool A and pool B. And what we do is that in pool A, we test with some like one tester, maybe we can go for one tester. But what happens is sometimes, like in most of the breeding populations, you will start with, let's say I have to cross my 1,000 fixed lines. So then I have to cross with one tester, and based on one tester, the estimation of GC effects and all those things will not be that much good. So we have to go for more testers. But as the number of testers will increase, your number of process for those, because first you have 1,000 into 1 is 1,000. But then you have 1000 into 2, 2000, then 1000 into 3 is 3000. So your number of processes will keep on increasing. And evaluating those large number of processes is very tedious and it's like getting very difficult. So same is the case with pool B. And once you have those pool A and pool B and you have the dash lines, then we go for hybrid development and like using the SCA effects as well. So what we do is sparse test processing. So it is one of the very promising strategies for early stage testing. Like we don't need to go for advanced stages. In early stage testing, we can cross with few testers in sparse design. So what is sparse design is, like let's say I have 1000 parental lines, inbred lines that I want to test, like I cross with the testers. So instead of crossing every 1000 with each tester, I'll just make a subset of those lines. 300 lines or 350 lines I can cross with one tester, 300 with the second tester, and the rest 300. So these are like different lines. And but the unique thing is we can see like here. So parent 1 into parent 2, we can see 2 lines are crossed with tester 1. Next 2 lines are crossed with tester 2. So this is the design. So what is genomic tool is helping in this is like this is possible due to the genomic information of the parental lines that is available. So what happens is that we borrow that genomic relationship. Now we know how line 1 is related to line 3, how line 2 is related to line 6, or like we know all the genomic relationship of those lines. So based on these process, like we can say, we instead of making 3000 process, we can go only 4000 process, and we can predict the performance of line 1 with tester 2, line 1 with tester 3, because now we have those genomic information available. So in the right side, we can see if we have to make only 1200 plots, we have the options of like single tester, that is like the common approach that was being followed, but sparse test processing design is giving us that flexibility. Like instead of making 1200 process or 1200 lines to be crossed with a single tester, cross 600 lines with 2 testers, that is one option. You can cross 400 lines with 3 testers, that is another option. So this gives us flexibility and it gives us like best GCA prediction. So if we see in the lower bottom panel, we can see that if we see at that mark, that is based on our phenomic prediction. But if we see plus 11%, so there is plus 11% higher accuracy in case of when we are going with the genomic relationship matrix. That is our genotypic data. Use of genotypic data on those lines helps in increasing our selection accuracy. And the second benefit is that if you see over the selection cycle, so the top one is cycle 1, the bottom one is the cycle 10, we can see that the genomic, these populations are getting quite separated over the time. And we can see from the PCA estimates that there is quite variability in our the breeding population that we are getting after 10 cycles of solution. So the overall is that it helps in making sparse test processing with few testers. So it helps in early stage testing, getting higher GCA prediction accuracy, and higher GCA prediction accuracy, as we already know from the Bidder's equation, if it is higher, then we will have higher rate of genetic gain. So 3 to 5 balanced testers that we can use instead of using more number of testers. So it gives us a optimum kind of solution that, okay, we are doing this on basis of some scientific approach. Then we have like, it helps us in rapid recycling of parents. So we can make decisions at the earliest stage, and again, we can shorten the breeding cycles, because if we can decide at the early stage, then we can again start our next selection cycle. So as already discussed, it helps in preserving genetic diversity within pools, and parental selection on base of GCA we can do that. And this is like multi-trait genomic prediction. So there are like unit traits. Sometimes we select based on only one trait, but there is another approach that is quite popular, that is multi-trait genomic prediction. And these approaches have come mainly from the animal sciences, because what happens is like in plant breeding we can replicate, we can generate progenies, replicate them. We have replicated data, but in case of animal breeding, they don't have that luxury. So in that case, what they do is they'll take multiple traits and they'll make some indexes. Let's say like there is milk production, or maybe there is like some protein quality, So there are different traits, or let's say in case of maize, we can go for grain yield, then we can go for, okay, I don't want anti-nutritional factor, so I can give a negative weightage that, okay, over the time, I'll not let this trait increase, or I'll want to decrease that trait. So based on that, we can make some selection index based on economic importance. Like grain yield, we can give highest weightage, then maybe, okay, plant height, we don't want to increase too much plant height, so we can give it a reduced weight, or maybe the flowering time. So we can give a weightage depending on what our objective where we want to take our breeding program. So here, what they do is they'll just take the multiple traits, they'll just have the genetic correlation of those traits, and based on those genetic correlation, we can give weightage. If a trait is negatively correlated, so we know like we will increase one, the other one is going to decrease. But there are options with the use of this genomic data that we can increase one trait by just keeping the other ones slightly constant, like it won't decrease too much. So there are some approaches in optimal contribution selection. So that takes of this, and there is successful example of using this BLUP, the best linear randomized prediction. So if we see that pre-BLUP, the period before introduction of these genomic selection, the index was increasing at the rate of 5.5 per year. But after that, the index is increasing at the rate of 16.5 index units per year. So the thing is that sometimes your multi-trait genomic prediction helps in gaining higher genetic gains. Sometimes they work, sometimes they don't work, because it depends on the genomic or the genetic constitution of the population that you are working on. So, so it gives us an advantage that it has better accuracy and genetic gains over unit trait selection, and it helps in simultaneous improvement of multiple traits. Multiple traits can be increased at a time, like on the positive side, or maybe one is increased and the other one you want to decrease. So it can do the same in that case also. And then it can help in increasing or sustaining the genetic diversity, because we know what to cross with what depending on our genomic relationship data. So one of the application from maize is, if we see in this figure, so what they have done is they have compared the phenotypic selection or the conventional breeding with the genomic selection. So if we see at the star mark that I have put here, so if we see cycle 2, C2, that is phenotypic selection, per se phenotypic selection. So there we can see gain is only 32%. But if you see at the test process based genomic selection, there is 59. Similarly, in the second scenario of drought, that is, there are two locations, CAP1, CAP2 are like two populations, and these have been tested for drought. So in the second population as well, we can see the phenotypic selection is 39%, giving 39% gain, but here we are getting 53% gain. So now it proves that with the phenotypic selection, we are getting overall like 30 to 39% gain, genetic gain. But in case of genomic selection, it is going 53 to 59%. So we can say it is like 10 to 20% better. And and as Dr. Srivastava has told that for drought conditions, like if we already have a genomic selection tool, we can predict and test our best to save our resources. Like if instead of testing 1,000 courses, we can go for the best 51 for the validation of field conditions as well. Then if we okay, I'll just take this screen. Then the next is targeted recombination. So this is one of the like I will say like AI based breeding. So this is one of the simulation based things that we'll be witnessing in the future. So what it gives is like we are combining here the genome editing, like the CRISPR test tools, with the breeding, with the genomic information. So just to have a brief is like, let's say we have a parent one, so its overall value is 0.2, because we have some negatives in red, we have some positives in the green. So these are like the different alleles that we have in one parent. So that combination of those alleles, negative, like favorable, unfavorable, it gives it a value of 0.2. but the second parent has a value of minus 0.3. But what if we can, combine the first two favorable 0.3, 0.9 with the favorable with the favorable from the second parent. So it can give us the DH line of 2.2. So we are getting a highly significant genetic gain. So this is possible with the help of the use of CRISPR system. So if we know, these are the genes, these are their defects, then we can go for precise manipulation for the targeted recombination. So just to explain a bit more is what if we can compare those scenarios? Like we are just getting response to selection without any targeted recombination. We haven't targeted anything. That means we haven't done any precise manipulation. So there we are getting 636 kg as the response to selection. But what if we can go with the targeted recombination? So we can see in the right, I have circled. So it is like we can just make the differences of what is best one out of 180, that is your phenotypic selection base. Then predicted performance, it is based on your targeted recombination base. So if we take those differences, we can calculate, we can see that we can achieve around 200% higher genetic gain with the help of this targeted recombination with the CRISPR-Cas9. And this also response to selection, we can see it depends on what traits we are targeting. It is not be like equally same for all the traits. It can vary depending upon the different traits. And this is my last slide. So this is like rapid development. So we have the different approaches, but the most important and widely used approach is the DH breeding. So DH development. So basically, the main important is like as I already said that we have to reduce the generation interval time. And to reduce the generation interval time, instead of like in conventional selection, conventional breeding, we used to select, we used to sell for like 5 to 6 generations, and then we used to get a fixed line, single line. But once we have a DA, we can easily get in 2 years, or maybe those fixed lines can be used for the next selection cycle. So what we do is that we have here the haploid inducer line, and we chose our lines that we want to use for the DS development. So we chose those lines with our haploid inducer, and then once we have haploid seeds, we go for the processing treatment, chromosome doubling, and we get instantly like 100% homozygous DS line. So nowadays, like if you see, since its evolution of this haploid inducer lines, previously we didn't have the haploid inducer lines with the higher haploid induction frequency, but now it has improved, and we have like over 10%, so 10 to 15% we can see from the CIMET also we can get those haploid inducer lines. And finally, these haploid inducer lines, like whatever we are using, it helps in reducing our breeding cycle. And other than that, we have the speed breeding that is also being used, and there is genome editing. So sometimes, let's say we don't have any option like how to create that variation in our line. So genome editing is one of the advanced tools that can be used. So in our institute also we are targeting different traits like milk architecture, VLSP resistance, and some others. And the final thing is the take-home message is that conventional breeding cannot be replaced, and conventional breeding can only be complemented with the genomic tools that are available with us. And the main thing that to be taken care by all the breeders is that we need to speed up the generations. We don't need to go for severe inbreeding in our populations, because if we go for severe inbreeding in our populations, then we are reducing the genetic variation. But the main thing is that everything depends on the genetic diversity. So we need to sustain our genetic diversity in the breeding program. So the final the conclusion is the breeder of yesterday selected the best based on phenotypic performance. Breeder of today, we are just predicting the best, like what is the best. And breeder of tomorrow will be designing the best. So with this, I would like to thank you all. And if there is anything, I will be happy to take up. हेलो रोमन सर।
थैंक यू डॉक्टर मुकेश। अगर किसी का अगर सवाल है तो पूछ सकते हैं डॉक्टर साहब से। एनी क्वेश्चंस किसी का? या चैट में कुछ आया है क्या? अगर अगर किसी का अगर क्वेश्चन नहीं है तो
So I think sir there can be two reasons. One is the topic is very like domain based. So it is like if someone is from the reading background can get it, but for others I think it not be not that convenient to get.
अगर किसी का अगर सवाल नहीं है तो डॉक्टर साहब बहुत बहुत धन्यवाद, आपने बहुत अच्छे से समझाया। और कल फिर मिलते हैं। एक क्वेश्चन आया है डॉक्टर साहब वो चेत में कि आई हैव बेसिक क्वेश्चन रिगार्डिंग जीवास एनालिसिस। व्हाट इज द मिनिमम पॉपुलेशन साइज रिक्वायर्ड फॉर जीवास एनालिसिस?
So Abhinav has asked, I think Abhinav has worked with us in our institute and he's in the research. So the basic thing is like there is no kind of criteria. It depends on sometimes you start with a crop, let's say like in quinoa. So the genetic diversity initially was very limited. So some researchers have started it with like 200, some have started with 250. So it depends on like how much you can handle. But the standard is like, okay, 300 is a very good population size for our training population, as well as for your jivas as well. And the higher the higher the size you will go on, it will be difficult to phenotype, and the genotypic cost will also increase. So the thing is that this question is like one has to decide on what are the resources available in your breeding program. So let's say if I have a project of 2 crores, then I can go for 500 lines. But let's say if I have a project of funding of only let's say 20 lakhs, I can limit it to 250 or 300. So, but the thing is that 250 to like 300 is a good number, and you can get like good accuracy and significant results with that. And if you go for the downside, then there will be like you'll be missing many rare alleles, and if you going for the higher side, maybe you will be getting the complexity of the population structure, because it depends on what is the genetic constitution of your the population that you have started working in.
I think that answer your question, Dr. Abhinav. अगर किसी का और सवाल है तो एनी क्वेश्चंस, एनी फर्दर क्वेश्चंस? अगर किसी का नहीं है तो बहुत बहुत धन्यवाद डॉक्टर साहब, एंड थैंक यू सो मच, एंड वी विल wrap up this session. Thank you so much.